Hello, thank you for joining us today. My name is Sarah Podsford. I'm the Content Marketing Executive at Erlang Solutions. Today we are joined by Barcelona-based cloud software architect, Jack Vanlightly. Jack specializes in event-driven architectures, data processing pipelines, and data stores, both relational and non-relational. He's no stranger here. Our past registrants of our webinars will recognize Jack, and today he's going to continue looking at the similarities and differences of RabbitMQ versus Kafka. This is part 2 in the series. If you didn't catch part 1, that's not a problem. It is available on YouTube and at our Erlang Solutions website under webinars. There will also be a part 3 in the series as well, so keep your eyes peeled on social media and websites for that. And you can also sign up to our newsletter for specific webinar emails. So one small thing before we start, if you are interested in RabbitMQ, there is a RabbitMQ Summit, which we are closely involved with. This will be held in London on the 12th of November. There's lots of confirmed talks, so the executive director of Goldman Sachs and lots of RabbitMQ experts as well. The early bird tickets are still available, so if you're interested, visit www.rabbitmqsummit.com. So before we get started, if you want to submit a question, you can do in the platform, and we'll have a Q&A session at the end. And please keep in mind that this is a live event, so we may experience some technical difficulties, although hopefully not today. Now let's get started. So over to you, Jack.
Good afternoon. Thanks, Sarah. This is part 2 of our RabbitMQ versus Kafka webinar series. And today the focus will be on reliable messaging. Whereas in part 1, we looked more at the underlying log versus queue and architectures. Today is all about the reliable, durable messaging and resiliency in the face of failure. How can we use RabbitMQ and Kafka as middlewares that can reliably receive, store, and deliver our messages? As usual, the answer is that there will be a series of decisions to make, each with a trade-off. Just like with many other distributed systems, we need to decide whether we will optimize for availability or consistency. The good news is that both systems give us that decision to make. We can go for a highly available, low latency, high throughput configuration that increases our risk of data loss and data duplication, or a highly consistent, higher latency and lower throughput configuration that aims to make message loss a rare case and minimizes message duplication. And there's a bunch of sort of space in between where we can kind of try and get a mix of the two. We'll also see that it's not just about configuring our broker, we also need to make our applications play ball. There's a shared responsibility from end to end between the broker and the applications need to behave in order to work reliably under various types of failures. So as long as everyone's cooperating according to plan, then we should get what we optimize for, whether that is availability or consistency. So my name is Jack Vanlightly. I'm a cloud architect and data engineer at CE in Barcelona. It's a consultancy firm. I'm currently working in Vueling Airlines in their data department. So I've been working on event-driven architectures, messaging systems, and these days I'm doing a lot of cloud automation and data pipelines. So before we get into the details of reliable messaging, I just wanted to cover first about the push and pull model that RabbitMQ and Kafka use. So RabbitMQ uses a push model where consumers open long-lived TCP connections and consumers register interest in queues, and the broker pushes messages down those long-lived connections in real time. Whereas Kafka has a pull model, so any given partition of a topic will only be consumed by a single consumer of a given consumer group. So that means that we can leverage batching, because where with RabbitMQ there might be competing consumers, with Kafka we have no such competing consumers, so we can use batching safely. So how it works is with RabbitMQ with competing consumers, we need to evenly distribute messages across all consumers, and we can only really do that by doing an even distribution of round robin message by message distribution. If we do large batches, then we can get quite uneven distribution amongst consumers. And also, if we do large batches with competing consumers, then the processing order doesn't really match the FIFO queue order. But with a push model, we need back pressure so that consumers don't get overwhelmed. And RabbitMQ provides the consumer prefetch, which limits the number of unacknowledged messages in flight at any given time. Whereas with Kafka, because we have no competing consumers, one consumer per partition, we can quite easily pull in large batches without worrying about distribution and without worrying about processing order. So that's why Kafka goes for pull and Rabbit goes for push. So message delivery semantics, we can go for at most once, at least once, or exactly once. So at most once means that messages might never get delivered. This is usually when we do no message acknowledgements. And so we send a message and it's fire and forget. Hopefully it'll get there, but we won't know. These tend to be the high throughput configurations, but not particularly safe. Then we have at least once, where we may end up delivering a message more than once, but it will have guarantees that we won't lose a message. And the holy grail is exactly once. And I might talk a bit later about how Kafka Streams achieves exactly once, but it is quite a limited scenario and not a general case for Kafka. Also, delivery may be the wrong word for the above terms. Instead, processing might be a better way of putting it. After, what we care about is a consumer can process a message, whether this is at most once, at least once, or exactly once. But using the word processing complicates things. Exactly once delivery makes less sense now, as perhaps we need to be, maybe a message needs to be delivered twice in order to successfully process it once. So it's one chain of responsibility. Producers, when the producer has the message, they are responsible entirely for the message and not losing it. But then they need to send that message to a broker, at which point there's a handover. And this is where a message is sent and acknowledgements are returned by the broker. In case of failures, the broker can communicate to the producer that it does not have it and the producer is still responsible. But once successfully stored at the broker needs to make sure it cannot lose messages even under different types of failures. And so the broker is 100% responsible for not losing the message once it's entirely under its own responsibility. And then there's another handover to consumers, which involves more message acknowledgements and making sure that the consumers use the acknowledgements correctly. And then once the broker has been informed that the consumer has the message, the broker can forget about it, and then it's just purely the consumer's responsibility. So with RabbitMQ, we have producer-side acknowledgements, and these are called publisher confirms. So we get different types of confirm. We get basic ACK, which is where the broker says, yep, I got it, no problem. Don't worry, I have it. Then we have basic NAC, which is saying that I got it, but there was a problem, and you should retry or something. And then finally, there's basic return and basic ACK, which is when we use the mandatory flag. And we'll look at that in the next slide. So we can batch acknowledgements, and the broker will batch acknowledgements if you give it a chance. When we send messages, we send each message with a sequence number. Each channel that the publisher opens with an exchange starts its sequence numbers from 1, which then monotonically increasing. And then the acknowledgements use those sequence numbers to acknowledge those messages. And we can use the multiple flag to group acknowledgements and send fewer acknowledgements, which helps for throughput. So mandatory, false, and true. When an exchange has no queues bound, or perhaps it has a topic exchange bound, but the routing key doesn't match, and the exchange cannot deliver the message to any queue. Now, by default, the mandatory flag is set to false. So this exchange will happily say, yep, I got it, and then discard the message. Now, in many cases, this might be okay. In a publish-subscribe architecture, where publishers are emitting events to the wider domain, letting them know if certain events have happened, other applications can be interested in those events, or they may not. And the publisher doesn't really care. It's just letting the wider domain know what's happened. And so in those cases, when there's no one listening that matches a particular message, it can be okay for it to be dropped. But when the publisher really does care about messages arriving at queues, we have the mandatory flag set to true, at which point Exchange says, I got it, but I couldn't deliver it to any queues. So it returns a basic return and a basic ACK. And this lets the publisher know, it needs to do something else. It might just log an error, or might store it in a database or something. Right, so we can get duplication on the publisher side. When we have large numbers of messages in flight, then we get higher throughput, but also higher message duplication when there are failures. So what does it mean that a message is in flight? That means that we've sent the message, but we haven't yet received an acknowledgement. So we can be sending messages one after the other, not waiting for the acknowledgements to come in. And so if the connection fails at that point, we'll never receive the acknowledgements for those 1,000 messages that are in flight. And so the publisher has to decide, well, what should I do? I don't know what happened to those 1,000 messages, so it might decide to resend them. Now, at the broker, the Exchange did manage to save 25% of the messages to queues. But the problem was the connection failed before it could send the ACKs. So it has 250 messages already in a queue. So when we resend 1,000, we now have 250 duplicates. So we could try and reduce the number of duplicates by lowering the number of messages in flight. So we can do that with the prefetch. So in the first example, we have a prefetch of, say, 1,000, and in this one, we have a prefetch of 1. And that basically means that, sorry, I'm talking about publishers here, not consumers. Sorry, we'll talk about prefetch later. This is where the actual publisher can decide when to pause for acknowledgements. What happens is you can decide to periodically just wait to get your acknowledgements. So what a publisher can do is it can send a message and then just block and wait for the acknowledgement to come back in. Now, this is terrible for throughput, but it's great for not getting too much duplication on the publisher side, because at most we'll get one duplicate. Now, one thing I tend to do is add a custom header. When I do resend a message, I add a custom header to indicate it's been resent. And this allows consumers to do some extra work to do any deduplication logic if they can. So consumer side, we have two modes for acknowledgements. We have auto ACK, and this basically is quite dangerous because the broker, as soon as it sends the message, it will remove it from the queue. So it's auto acknowledged. It's basically fire and forget. So if the connection fails, it's possible that the message didn't even arrive at the consumer, but it will still have been removed from the queue. The other danger is that it can overwhelm the consumer because it will go as fast as the TCP connection will allow. Now, if your consumer is processing the messages slower than TCP connection allows, then you can overwhelm the consumer and fill its buffers to breaking point. So manual acknowledgements are preferred, and we can do grouping of acknowledgements with the multiple flag to improve throughput. So there is the basic ACK, as always. So, the consumer tells the broker, yes, I've got it, you can remove it from the queue. There is a basic NAC with redeliver equals false, that's a flag, and you're basically telling the broker, I got it, but an error happened, but just remove it from the queue anyway. Then you have a basic NAC with redeliver equals true, which basically says, I can process it and it needs to be redelivered. Now, if there's only one consumer on the queue, it will get redelivered to the same consumer. And if there are multiple competing consumers, then the message will be delivered to any one of those consumers. There's also basic reject, which is like basic NAC, but without multiple flag support. So the multiple flag is great for throughput. We can basically, if we've processed 10 messages, we could, in a single message, just put the multiple flag as true and a basic ACK of 10. So just like with the publishers, we have a monotonically increasing integer, which is identifying the messages. But instead of it being called the sequence number, it's called the delivery tag. Now the redelivered flag is set on the message by the broker. So what happens is, let's just say the broker pushes a message to a consumer. The consumer can't process it for whatever reason, and it responds with a basic NAC and redeliver equals true, at which point RabbitMQ will then deliver that again. Perhaps it goes to a different consumer, and that consumer manages to process it and responds with a basic ACK, and everything's okay. And now what's nice is that because we get a redelivered equals true flag, we can actually perform extra deduplication logic if we want to, because sometimes deduplication logic is expensive, and we only want to do it when we know it's been redelivered. Because not all operations are idempotent. I know that if you can make it idempotent, and it doesn't matter about duplicates, but when you're sending emails, you know, that kind of thing is not idempotent. So consumer side duplication is very similar to producer side duplication. So again, if we have a large number of messages in flight, we can get high throughput, but we get more duplication on failure. So here we have a prefetch of 1000, which basically limits RabbitMQ to sending 1000 messages or having 1000 messages unacknowledged at any time. And if the connection fails, then it will redeliver immediately all those messages again. And so perhaps the consumer had processed a bunch of the messages, but was unable to send an ACK because the connection failed, at which point now we get quite a lot of message duplication. Now we can decide to have a prefetch of 1, where RabbitMQ will send a single message and wait for an ACK. We send an ACK, it will send another message, we send an ACK, and the connection fails. And at most we could ever get is 1 message duplication, but you get lower throughput. So it's really down to your use case. So broker durability. So once a broker does have a message, it's responsible for not losing it. So we have a few different concepts here. We have durable queues, persistent messages, and mirrored queues. So what that means is that a durable queue, when you restart a node or bring it back after it's failed, if it's marked as durable, it will be redeclared. If it's declared as non-durable, it will be deleted on restart. So if you want your infrastructure, your queues and exchanges to come back after a failure or after a restart, you need to mark them as durable. Now, just because your queue gets redeclared doesn't mean to say your messages come back. Messages can either be non-persistent or persistent, and it's the publisher who decides. So if they're non-persistent, when a broker comes back online, they will be deleted. If it's persistent, they will be brought back to life, and the queue will be in the same state it was when it failed. Then there's mirrored queues, which is what we want when we want to make sure that any node can fail and we continue with availability and without data loss. And that's when we have a cluster of multiple nodes. So just reiterating what I've just said, we can have broker restarts or we can have catastrophic broker loss. And depending on whether your queue is durable, whether your message is persistent or non-persistent, and whether you have a single queue or a mirrored queue, it depends on whether you'll survive different restarts or catastrophic failures. So the most safe is a mirrored queue with persistent messages. So let's have a look briefly into Qmirrors. So here we have a cluster of 3 brokers and we have 4 queues. We can set up Qmirroring very easily through policies. QA has a policy of HA mode all, which basically means that we have a master queue where all reads and writes go to. All messages get written to master and all messages are read from the master. The mirrors are just there for redundancy and for failover. So when we have HA mode all, we have mirrors or a master on every node. Or we can say exactly 2, like in QB, or exactly 1, like in QC, or an unmirrored queue where we have QD. Now, let's just say we lose broker 3. QC had its master Q on broker 3. So what happens is the oldest mirror gets promoted, and that happened to be on broker 2. So broker 2, now QC has its master. Then we lose broker 1. Let's say it's a catastrophic failure, the data, everything's gone. We fail over QB to broker 2, the master, and now we have all the masters on a single broker with no redundancy. So we bring back broker 1. Whether or not it had been catastrophic or not, mirrored queues throw away all their data on start, and then they need to be synchronized or not. And we'll look at synchronization in a minute. But basically, they start from scratch. Then we get broker 3, and we see that RabbitMQ makes sure that the policies are respected and that we continue with the same amount of replication factor. So synchronization and queue failover. Let's have a look at 2 examples here. We have 2 queues, and this is where we have our HA sync mode. Now there's 2 options. We can have automatic or manual. And we're going to see exactly what this is all about. But synchronization is basically about the behavior when a new mirror comes online, whether or not it's synchronized with the master immediately or not. So we have QA and QB, each has a master on a different broker, and each has 10 messages. Then we lose broker 3. So far, no problem. The masters continue to receive writes and reads, just that our redundancy is reduced down to 1. Then broker 3 comes back. So what happens is that the QA mirror on broker 3 is immediately synchronized with the master. Okay, so now we're back to redundancy of 2, whereas QB on broker 3 stays at 0 because the synchronization mode is manual. So right now nothing will be synchronized, which means that it does not contribute to redundancy for the existing messages. All new messages that come in will be routed to broker 3, but existing messages are not. So broker 2 fails, and we have QA, its master queue is on broker 2. It does a failover to broker 3 without message loss. We also, before broker 2 failed, we had received 10 more messages to each queue. So now they've got 20 in each. And you'll notice that on broker 3, QB, the mirror has only 10 messages. And that's because we never replicated the existing 10 over. Now we lose broker 1. So we received 10 messages before broker 1 went down. So QA has 30 messages and QB had 30 messages, but then broker went down, and because there was only 1 broker left, broker 3, it failed over to QB. But this is only the case when HA promote on failure is equal to always, which is the default. So basically it means that we can still fail over to an unclean, sort of stale mirror, but it does mean message loss. So this is where we want availability over data consistency. So we're happy to, well, not happy, but we're willing to lose a few messages in order to stay available. Now, if we just imagine that we hadn't had HA promote on failure policy to always, instead we had it on when synced, we would have seen that QB would have become unavailable because it would not have failed over because it was unsynchronized. And then we have a queue that is unavailable. So it's all about, and then maybe we can bring back broker 1. Maybe we didn't lose the data, maybe just the server crashed or something, and we can bring it back online, and the master will resume on broker 1, and we'll have the 30 messages, and we can continue. So without data loss, but a loss of availability. So you might be thinking at this point, why would I ever choose manual synchronization when I can have automatic synchronization? Well, consider this case. Here we have a queue that is not active, or maybe it's just consumers are running a bit slow and we have high volumes, and our QA and QB both have 100 million messages, okay? So broker 3 fails again, no problem. We still got redundancy of 1. Broker 3 comes back online. Now with automatic synchronization, the QA will immediately synchronize the 100 million messages to the new mirror on broker 3, because although broker 3 had 100 million already, it threw all those away when it came back online, and it needs all of the 100 million again. And when RabbitMQ is doing this synchronization, it makes that queue unavailable. Okay, no one can connect, no one can send or receive from that queue during that process. And if it takes minutes or hours or days, then that's how long they have to wait. So now you're seeing maybe it might be a bit dangerous if you've got very large queues. Whereas the second queue, QB with manual mode, is quite happy. It's still available. We've really only got a redundancy of 1 for the existing messages, but we can continue to receive messages without a problem. And sometimes availability is better than data redundancy, because if you're in a situation where publishers can't really do anything else except drop the messages, then availability is better. And then finally, maybe a few hours later, the synchronization is finished and QA becomes available again. So we can optimize for high throughput. So on one extreme, we can have producers fire and forget. Consumers can use auto ACK mode. We can have non-persistent messages as they reduce load on the brokers. We can not use mirrored queues, and we can have a cluster, but for throughput. So we can distribute load across 3 nodes, for example. Or we could go for a balance of data safety and high throughput. Producers can wait periodically for acknowledgements. Consumers can group acknowledgements with the multiple flag. We'll go for persistent messages that allow us to enable restarts and failures. We'll use a cluster with mirroring of 1, which gives us a small amount of redundancy, but without causing too much load. Or we can go full on for data safety, and we can make sure that we are waiting after every message for acknowledgements. Consumers are acknowledging every single message to reduce duplication. We have persistent messages. We go for a cluster with queue mirroring of at least 2 mirrors. We put promote on failure when synced to avoid failover to unsynchronized mirrors. And we have automatic synchronization for active queues. So if you have an inactive queue that has hundreds of millions of messages, then automatic synchronization could be quite dangerous. Whereas if you have active queues that are actively being consumed, that even with high throughput might only have a small number of messages, then automatic synchronization might be better for you. And we're going to look in part 3 about network partitions, slow network links, and flaky links. See how RabbitMQ behaves when it's in a split brain, where a cluster is split in 2, and you end up with 2 queue masters. We don't have time to look into that today. Right, let's jump over to Kafka, and we'll look at how Kafka deals with producer-side acknowledgements. So first of all, we just need to briefly have a look at leaders and followers. So Kafka was kind of built from the get-go to be sort of replicated, whereas that was introduced later onto RabbitMQ. And so each topic can have multiple partitions, and each partition will have a leader and 0 or more followers. In this case, we have a single topic with a single partition, and we have 1 leader and 2 followers. And the followers are polling the leader for the latest messages rather than getting pushed from the leader. So they're there every 500 milliseconds requesting the latest data. So on the producer side, we have producer configs, and we have also broker and topic configs that affect reliability. So on the producer side, we have acknowledgements. X is the alias, and we can set it to 0, which basically means fire and forget. We will not wait for any acknowledgements. We can have X equals 1, which will mean that the leader has persisted the message. And we can have X equals all, or -1, and that means the leader and all in-sync replicas have persisted the message, that the message is committed. So we'll talk about an in-sync what the in-sync replicas are, but you can think of it as the list of replicas that are up to date with the leader. And so AXI was always much more safe, but again, introduces more latency. Other settings that are important are retries, enable idempotence, max in-flight requests per connection, and we'll look at that in the next slide. And other settings are the replication factor of a partition, of a topic. So the more followers you have, more redundancy, the more fault tolerant you'll be. The min in-sync replicas, which will protect us from being in situations where we only have a single replica with data, and we'll look at that very soon. And we have unclean leader election enable, which allows us to fail over to unclean followers, and that basically means stale followers. Just like with RabbitMQ, we can do that. So one note of caution, the libraries you can configure to do automatic retries. Now, if you have retries and you have multiple requests in flight, then you can end up with message duplication and out of order messages. So, Kafka provides very strong ordering guarantees with its partitions, but if you send them in the wrong order, there's nothing it can do. So let's have a look at an example here. We end up sending 3 batches to 3 different partitions, okay? And we end up getting failures on batch 1 and 2 on partition 0, but batch 3 is okay. And on partition 2, batch 1 has failed, but batch 2 and 3 have been appended okay. So at this point, we can retry. So we resend batch 1 for partition 0, we resend batch 1 and batch 2, and now we're also sending 4 and 5. And on partition 2, we're resending batch 1. To complicate things further, partition 0 did actually manage to save the messages of batch 1, and so it just wasn't able to communicate that before there was a failure. So we end up on partition 0 with messages in the order of the messages of batch 1, then 3, then 1, then 2, then 4 and 5. So not only do we have duplication, but we're out of order. And this could also affect RabbitMQ. So retries can be dangerous. So if you really care about message ordering, then you can do retries and just have multiple requests in flight to 1, which does severely reduce throughput. So it's always a trade-off. Now, we can avoid data loss on the producer side and avoid duplication by using that enable idempotence equals true. And so what this does is the broker will actually keep track of the messages sent by each producer and is able to detect duplicates and just discard the duplicates. But there are some limits. We need to make sure there's 5 or less max in-flight requests per connection. Retries must be set to 1 or higher, and ACKs must be set to all. But this is pretty handy, a nice way of just avoiding duplication while still using retries when there are failures. So let's have a look at how replication works and failover. So here we have a single topic which has 4 partitions, and we see that the leaders are nicely distributed amongst the 3 brokers. And because it's just a single topic, the replication factor of the topic is applied to all 4 partitions. So let's have a look. When broker 3 goes down, we do a failover to partition 2 on broker 2. Okay. And when broker 1 goes down, the leader on partition 1, which is on broker 1, is failed over to broker 2. And so now we're in a situation where we have no redundancy and all our leaders are on the same broker. We bring back broker 1 and the followers, those partitions are now followers. And we bring up broker 3 and those partitions are now followers. And they're all following the leaders on broker 2, which is not ideal because that means that now all the publishers and consumers are all needing to open connections to broker 2, which is not going to be great. So we have a couple of options here. We can use the auto leader rebalance enable equals true, and that will basically automatically rebalance our leaders according to preferred leader. So you can set preferred leaders. Either Kafka will do it for you, or you can do it manually, and then Kafka will automatically rebalance leadership as brokers come and go to try and keep it nicely distributed. There's also a tool you can use, the Kafka preferred replica election shell script, which can do it manually for you. So let's get to the in-sync replica set, because this is very important, the ISR. So the ISR consists of the leader and all the followers who are up to date with the leader. So what does that mean? So we have a replica lag time max milliseconds setting, okay? So what that means is if a follower has not sent a fetch request to the leader in that time, it is considered dead, okay? And it is removed from the ISR. Or if it's a slow replica, if it's been out of date for more than this replica lag time max milliseconds, it will also be removed. Now, by default, this is 10 seconds. So the leader and the followers know where they're up to. So the leader has a high watermark, which is the committed offset. And so it knows when followers make requests, make fetch requests, it knows what offset the followers are at. And so it will know if it's out of date. And if it's out of date for more than those 10 seconds, it removes it from the ISR. Okay, so why does it do this? What does the ISR give us? Let's have a look at an example. So now we have a topic with two partitions, okay? We have one message a second arriving, or maybe a better example would be 1,000 messages a second or 1,000,000. But we have a message arriving at our leaders. So we can see that broker 3 is lagging, okay? It's 8 seconds or 8 messages or 8,000, 8 million messages behind the leader on partition 1, and on partition 0, and on partition 1 it's 9 seconds behind, okay? So that's either because it hasn't sent a fetch request in 9 seconds, or it's been out of it's not been up to date for 9 seconds, but it's still just within the bounds of the ISR. And so but when it falls out of that range, now it's say 22 seconds behind, it gets removed from the ISR. Okay, so let's just, perhaps broker 3 is having some problems, perhaps it's having a lot of garbage collection, or there's a problem with the network link, or high CPU utilization, or something that's slowing it down. It gets removed from the ISR. Okay, so we will get to now why the ISR is important. So this is one configuration where we're going to optimize for low latency and high availability, but not data safety. Okay, so let's just use one single partition as the example. Okay, so the producer says, right, sending you a message, and it sets the ax equals 1. So that basically means that it only requires the leader to have written it to its log. It does not require the followers in the ISR to have also written it. Okay, so even though partition 0 on broker 3 is right now 8 seconds of lag, the leader is able to send an ACK as soon as it's written to the local log. So it's getting 0 extra milliseconds due to the replicas. Okay. Now we lose the connection to broker 2. Broker 2's gone down. Okay. We lose one message in the failover, because although broker 1 is closer to being in sync, it still wasn't in sync. It had not got that message, and we've just lost a message in failover. So this is the risk of using ax equals 1, because during failovers, the risk of losing data is quite high. But the latency is very low. Okay, so the producer now is able to find the new leader and start sending its messages. And now broker 3 is still in the ISR, and it's still going slow, but it doesn't affect latency, because we still only writing messages to the local log. Now broker 3 is removed from the ISR because it's lagged too far behind. It's now been 14 seconds that it's been out of date. Okay, but we're in dangerous waters here, because we have only a single replica that has all the data, okay? Now we have unclean leader election enabled to true, which means we can fail over to a replica that has not got all the data, okay? So broker 1 fails, and we do fail over to broker 3. And while doing so, we've just lost 15 messages, okay? But we continue to be available. So we get a quick connection error, but there's no problem. The producer reconnects, now finding that the leader is on broker 3 and continues to send its messages. So while we lost data, we continued to be available. Now let's look at another extreme where we are going to go for data safety, but we're going to have increased latency and lower availability. So ACKs will be all, replication factor of 3, and min in sync replicas equals 2. This basically means that if the ISR shrinks to 1, that basically means the leader is the only replica that is up to date because it's the leader, then it will refuse to accept messages until the ISR is larger. But we'll have a look at a concrete example. We've got ACKs equals all this time, okay? Now, broker 3, poor broker 3 again, is lagging. Again, it's averaging about 4 seconds of lag, okay? So we send a message. Now the leader writes the message to its local log straight away. And within under a second, broker 1 has it, but broker 3 still doesn't have it. It still doesn't have it. And we end up waiting 4 seconds for an ACK to that one message because of a slow replica. You'll see now that broker 3 is up to date because it just made a fetch request and now it's got all the data, so it's fully up to date. But it was lagging. It took 4 seconds of extra latency for the ACK to occur. Okay, now broker 3 again is falling behind and it's just going slow, and now it's 14 seconds behind, and so it's got removed from the ISR, which is good news for latency because now the leader, broker 2, does not have to wait for the slow follower to catch up. It just removes it from the ISR, and now with the ACKs equals all, it only has to wait for broker 1 to say it's got the message. And broker 1's going pretty quick, ends up having to wait 250 milliseconds for it to confirm it's got it, and then it sends an ACK. So we get, so the benefit of the ISR is it allows us to replicate our data and give guarantees that multiple replicas have our message, but as well not suffering from slow followers. Slow followers can only penalize up to a certain point before they get removed from the ISR, and then they don't penalize performance anymore. So broker 2 goes down, connection error, and we fail over to broker 1. Now, because broker 1, we had ACKs equals all, broker 1 has all the messages. So we've just managed to do a failover without message loss. So remember that when we had ACKs equals 1, in the previous example, we'd end up losing messages, even for a follower that was reasonably good at staying up to date. But now we have danger. We have one leader, and that's it. We have an ISR of 1 node. Now, broker 3 is way behind. If broker 1 were to fail now, we'd lose data. So if you don't want to expose yourself to that risk, if it's unacceptable for you to have messages because they're so important, only exist on one broker, then that's why we have the min in sync replicas equals 2. So what will happen now is the producer sends a message saying ACKs equals all, and the broker will respond with not enough replicas because it doesn't have enough replicas in the ISR. And broker 3 finally catches up, and now it's able to acknowledge messages because broker 3 has joined the ISR, and the ISR is 2, and so it can now respond. Now, if we had min in sync replicas as 1, if we go back, then what we would have seen is it would have said, okay, even though the ISR was only 1 node, and the producer is saying only respond with an ACK once all the in-sync replicas have received it, while all the in-sync replicas was just the leader. So it would have returned an ACK saying great, but it is at risk now because it's the only copy. So that's why we use min in sync replicas. So, and finally, we'll look at consumer offset tracking. This is similar to the consumer side message acknowledgements, except we're just committing offsets. So we can read large batches of messages, and then we can use an auto commit, like a periodic commit, which is every few seconds committing the offset, okay? Or we can do manual commit, and the manual commit gives us full control over when we commit our offsets. So if we have auto commit on a long period, it's great for throughput because we're not having to send too many messages, too many requests to the broker. But in case of failure, we can get a large amount of duplication. Now we can go for short periods or manual commits where we're committing every message, but bad for throughput, but great for avoiding duplicate processing. So again, it's very similar to RabbitMQ really. When we have 1,000 messages in flight and the consumer fails, and it didn't commit the offset, then a replacement consumer will come along and it will say, oh, what's the offset? And because the failed consumer, although it had pulled a batch of 1,000 messages, and although it had processed 25% of them, it had not committed the offset, that it had not committed that it had processed 25%. And so the new consumer that comes along just ends up fetching the same 1,000 messages and ends up reprocessing 250 messages. So, high throughput, high message duplication and failure. Or we can pull in a big batch again. We don't need to pull in message by message, but what we can do is we can commit much more often. And at an extreme, we can commit after every message. So we pull in a big batch of say 1,000, and then we do commit every time we process a message. And that means that if that consumer fails at any point, the replacement consumer that comes along will say, hey, what's the offset? It will get an offset and perhaps just only duplicate, reprocess one message. So again, it would be great today to have looked into network partitions and split brain and everything like that, but we don't have time, so we're going to be covering that in part 3. So to round up, both systems give you the necessary knobs to give you what you want, whether it's availability or consistency. It's a series of decisions with trade-offs, which depend on what you want to optimize for. So they both are very tunable. Do you want consistency or availability or low latency or high throughput? You can tune it according to your needs, but there are trade-offs. You can't get everything that you want. Then they both use message acknowledgements. They have configurable redundancy. Where they differ a bit is that the replication in RabbitMQ is synchronous, and in Kafka you can do it synchronously, where you use the all x equals all, where you wait, the producer waits, or asynchronously, where maybe you only wait for the leader or you don't wait at all. In RabbitMQ, replica synchronization can cause unavailability, okay, which can be a headache. There's a hard decisions to make there, whether you use automatic or manual synchronization. Whereas with Kafka, we get no such unavailability, though you can still saturate your network with when you create new replicas that are following that need to replicate. But because they stay out of the ISR until they're fully replicated, they just sit there in the background, and all they do is end up consuming some resources, but they don't cause unavailability. Then on the consumer side, on RabbitMQ, we get the redelivered flag to indicate when something's been redelivered, which can help avoid duplicate processing. And on the Kafka side, we have idempotency on the producer side, as long as you set those configuration settings. It does reduce throughput, but if you really want to avoid duplication, it's very handy. And finally, we can do fire and forget on both, or with RabbitMQ, we get publisher confirms, which we then wait synchronously for all mirrors to have received the message. Whereas with Kafka, we get a few more options. We can say leader only or all the ISR. In addition, we can say the min and sync replicas as well. So that's it. If you have any questions, I'm happy to talk about anything I've covered here. Or if you have any other questions, including things like network partitions, we will go into that in the next part. But if you have any questions, I don't mind answering that now.
Yeah, thank you, Jack. That was a fantastic webinar. And just to remind all of our registrants that it will be sent out to you via email, so keep your eyes peeled for that. We do have a few questions, Jack, if you've got time. So the first question is, when do you think RabbitMQ is best suited, or better suited than Kafka?
That's very difficult. That also comes down to architecture, like we covered in the last part. You know, sometimes RabbitMQ, the flexibility of RabbitMQ is its killer feature, because you can decouple your producers from your consumers very easily behind routine and exchanges and queues, and you can have each application creating its own queues and configuring routine to exchanges, and you have real decoupling. You can evolve your architecture really easily. There's less hard decisions on your architecture, your event-driven architecture with RabbitMQ. Whereas with Kafka, because topics are more like shared infrastructure, you write to a topic and you read from a topic, so they're more shared infrastructure. So you really need to start thinking about things like that. So I mean, I could talk for a long time about it's a bit wide, the question.
Yeah. So second question, does each technology have a similar PaaS cloud counterpart?
So you have Cloud AMQP for Rabbit. Okay, that's the big one for RabbitMQ, and for Kafka you have Confluent, who are they're the owners of Kafka, and you can set them up in your AWS or wherever you need, and they both take away the headache of having to manage these distributed systems, which can be complex to run.
Okay, brilliant. Thanks, Mark. We've got one last question. So what kind of support contracts are available for each technology?
I don't know about Kafka, because we use managed. We use PaaS for that, but we have RabbitMQ on premise, and so Pivotal provide a support contract where if we have any problems within a few hours, they will respond and can come on premise when needed. I can't really give details of price and things like that, but I do know that Pivotal will provide you on-premise support contracts. I'm unsure about on-premise Kafka though. I'm afraid I have to look that up.
Okay, brilliant. There's nothing else from our end here. I don't know if there's anything else you'd like to add, Jack.
Not really. We'll be covering in the next part, we'll actually be doing more of a demo, and we'll actually be doing, it should be a lot of fun. We're going to set up a cluster of Rabbit, and we're going to set up a cluster of Kafka, and we're going to test out the different configurations, how we look at the strategies for dealing with network partitions and slow links, and seeing what kinds of data loss we can provoke, and just seeing some of the failure modes of both clusters. So should be a lot of fun.
Yeah, that sounds brilliant. Yeah, we'll be sending out more information about that, so don't worry, you'll see it on our social media and things like that as well. So for now, bye-bye, Jack, and we'll speak soon.
Okay, thank you very much.
Thank you. Bye.
Bye.